So let's just summarize what we did last time. We said, well, I want to compute trig functions of pi over 6. So let's draw, oh, Jesus Christ. It's a really nice feature that when you open HoverCam and then tell it you want to record, it immediately closes the window that HoverCam is in, so you have to open that back up. Anyway, so, oh, by the way, happy November Fool's Day. So we said we want to compute trig functions of pi over 6. So we drew this triangle that has an angle of pi over 6. You may as well normalize it so the hypotenuse has length 1. So just label out hypotenuse with a 1. If you can determine the other side lengths of this triangle by doing some geometry, then you know trig functions of pi over 6. And we started doing that. We noticed that, well, if you double this triangle, you get yourself an equilateral triangle. So all those side lengths are the same. In particular, that whole side length has to be length 1, because the hypotenuse has length 1. Well, once you know that, well, that means b plus b has length 1, so the side length b had to be a half. We used that and concluded that sine of pi over 6 would be opposite over hypotenuse is 1/2 over 1, also known as 1/2. Even without knowing the side length that's called BA in that triangle, what other trig function can you just know already by looking at this? In particular, look at that pi over 30. So this angle is pi over 30. Do you know the adjacent side length to this pi over 30? Yeah, it's that 1/2. Do you know the hypotenuse? So which trig function do you know? Yeah, you know cosine. So what is cosine of pi over 30? Well, it'll be adjacent 1/2 divided by 1. 1/2 divided by 1 is 1/2. Cosine of pi over 30 is 1/2. All right. All of the other trig functions will require me to know this horizontal side length, the side length called A. Do I have enough information to determine A? In fact, did we determine A last time? Am I looking at the other section's notes? I am? Okay. Let's look at the correct notes. Ah, there we go. The side length A was √3 over 2. How did we get that √3 over 2? What was the trick? What was the tool that we used to get that? Yeah. This squared plus that squared equals this squared. If you know these two, you can solve for that. All right, so let's determine the other trig functions. By staring at this triangle then, tell me, what is, I guess pi over 6 is the one that I should do first. What's the cosine of pi over 6? Well, cosine is adjacent over hypotenuse. There's the angle pi over 6. What's the adjacent side length? What's the hypotenuse? So it's the cosine of pi over 6. Tangent pi over 6. What's the, so tangent is opposite over adjacent. Tangent of this is opposite over adjacent. So it'll be 1 over 2 divided by √3 over 2. Does that simplify it all? I think so. In particular, I see a fraction divided by a fraction. Your final answer should never be a fraction divided by a fraction. You should simplify. How does it simplify? and now I see a square root in the denominator. That still makes me unhappy. I should not, in my simplified answers, I don't want to see square roots in the denominator. How do I get that square root out of the denominator? Multiply by root 3 over root 3. But you can always multiply and divide by the same thing. That doesn't change the answer. Picking the right thing to multiply and divide by is how you simplify the same thing. Multiply by root 3, divide by root 3. Root 3 is root 3 squared, or 3. Root 3 over 3. So I'm going to encode that in these lines. Cosine of pi over 6 appears to be root 3 over 2. Tangent of pi over 6 is root 3 over 3. And let's also encode that in this. So we just did computations at pi over 6. That tells me these points. Cosine is root 3 over 2. Sine is 1 over 2. Tangent is root 3 over 2. All right. That seems pretty okay. So this is, I think, a really nice example of having two different philosophies with trig functions. You can use the triangle to make some computations. Once you've used that triangle to make computations, you also know units all facts. Let's just finish that out. Do I also know enough information to compute trig functions at pi over 3? Yeah, tell me, what is sine of pi over 3? Square root of 3 over 2 divided by 1. There's this angle pi over 3. Or, if you like, there's the angle pi over 3. The opposite side length is A, which we found to be root 3 over 2. Hypotenuse is length 1. Oh, we already did that. Okay. What about the cosine of pi over 3? What should that be? 1/2 divided by 1, also known as just 1/2. How about tangent pi over 3? Anything simplify? So that's just root 3. All right, cool. Let's encode that in the unit circle. At an angle of pi over 3, you get an x value of 1/2, because that's cosine, a y value of root 3 over 2, and a tangent of the square root of 3. That seem all right? Nice. So, what I want to do with today is I want to start talking about graphs of trig functions. And I want to make one thing perfectly clear. The unit circle has to do with trig functions, right? Is that itself the graph of a function? No, it fails the vertical line test. Everywhere, basically. So when I talk about the graphs of sine and cosine, I don't mean the unit circle. But let's see what I do mean. And I think you can figure one thing out pretty quickly. So let's do a multiple choice question. This isn't in the notes, this is slightly impromptu. Here are 4 functions. This one is called A. The pink one is B. And you don't necessarily need to draw this down. This will be relevant in a moment. The green card is C. And let's see, one of them has to be D, right? Blue, green, pink is B. The red one must be D. Let's call the red one D. I will tell you for a fact that one of these is the graph of sine, another one is the graph of cosine, the other two are something else. So by staring at those graphs, which one do you think should be the graph of, is sine the one I asked about first? which one of those might be the graph of sine? Oh, even let's go with partial information. Is there one of those that you know cannot be the graph of sine of x? Let's start with this. What's the sine of 0? Pull out your unit circle if you like. I can't because this is not now on the back of my unit circle. So you start at 1, 0. You rotate by an angle of 0. What's the y coordinate where you land? 0. So what's the sine of 0? 0. Sine is the y coordinate. So sine of 0 has to be 0. So the graph of sine of x must pass through the point 0, 0. Which ones can I eliminate from contention for being sine of x? A and D? Yeah. Y equals sine of x cannot be A or D. All right. What's something else you know about sine? Possibly by looking at your units offer. What is another value you know that sine takes? How about pi over 2? What's the sine of pi over 2? Here are 1. Pi over 2 is a right angle. So if you start at 1, 0 and rotate by a right angle, you wind up with a point that has y coordinate 1. So sine of pi over 2 has to be 1. All right, so I guess I haven't given you enough information here to see like where the x values are, but maybe I'll tell you this. That happens at x equals pi over 2. So, of all of the functions provided, which one seems to go through x equals pi over 2, comma y equals 1? C. So, it sure looks like y equals sine of x is the green one. C. Could we play the same game with cosine? Probably. Let's play the same game with cosine. What's the cosine of 0? I hear a 1. People agree? All right. So, that means y equals cosine of x must pass through x equals 0, y equals 1. Which ones can you eliminate based on that? All of them except A? Oh, cool. That's enough. So, y equals cosine of x is the graph labeled A. What do the other two functions seem to be? I'm particularly bad at reading lips today, so if you want to, like, say your answer, go for it. The red card. How does the red card seem to relate to other things on this? Say that louder?
Opposite of A.
It's the additive opposite of A. So that means the red card looks a lot like it's just negative cosine? Yeah. D sure seems to be negative cosine of x. Because it sure looks like it's the same as A, but flipped over the y-axis, x-axis. All right. I guess B is still unaccounted for? What does it seem to be? Yeah. Not just sine of 0. It should be something having to do with the x value somehow. But yeah, this b, which, it's something flipped over the x-axis. Which curve would you want to flip over the x-axis to get pink? C. So the one that is sine of x. So I want to take sine of x and flip it over the x-axis. So it sure looks like this is just negative sine of x. Feel pretty good? All right. So let's start in on the actual notes for today. Let's talk about graphs of trig functions. So right here, we see the graphs of sine of x and cosine of x. And you know what? Even though we've literally just done a Herder multiple choice question, one of those is sine, the other one is cosine. Which one should this one be? Sine of x. Because it passes through 0, 0, sine of 0 is 0. So I guess this next one must be cosine of x. And let's just check that. It passes through 0, 1. Should it pass through 0, 1? Maybe we'll check this point too. Apparently it passes through pi over 2, 0. Is the cosine of pi over 2 equal to 0? Awesome. All right, so let's read some things off of those graphs. And maybe we'll just go top to bottom. Let's optimize. What are the maximum and minimum values these functions take? What's the maximum value? 1. The biggest y value you see on either one of them is 1. And I guess that makes sense. Cosine is the x value on the unit circle. Biggest x value you see on the unit circle is 1. So the maximum value of these is 1. Let's list some inputs that achieve that output value. Now let's focus on cosine first. Tell me, what are some inputs that result in cosine being equal to 1? So, here's the graph of cosine. What are some inputs that result in a cosine of 1? Yeah, 0 is definitely one of them. Is there another? 2 pi. Is there another? Negative 2 pi. And I guess those are all the ones that you see on this picture. If I continued this picture, would there be more? Yeah. What's the next place that you think it would happen? Ball pi. And I guess also negative ball pi might happen. In fact, do you think any even number times 2 pi would do? Oh, nice. So in general, I guess the formula for that would be 2k, because that's the formula for an even number, times pi with k a whole number. How about sine? When is it equal to 1? Let's play that same game. What are the inputs you see where sine is 1? I hear pi over 2. Any other inputs? Negative 3 pi over 2. Do I hear any other inputs? I guess these are the only ones you see here. But it sure looks like if you continued this on, it's going to get back up there. And maybe the best way to see it is, let's go back to the unit circle. An angle of pi over 2 results in the sine of 1. But I could also go around the unit circle an extra time, or an extra time after that. Or I could go to pi over 2 and then go backwards by 2 pi, and backwards by another 2 pi. So I think in general, the right way to write this is anything of the form pi over 2 plus 2 pi k. Those are all the places where sine achieves its maximum value. Feel pretty good? Should we also minimize? What's the most negative value sine takes? Oh, should I start with cosine? Let's start with cosine. What's the most negative value cosine takes? -1. Can you start listing some inputs where that happens? -pi, it happens. So at x equals -pi, or x equals pi. Any other inputs where it seems likely to happen? I guess not in the picture provided, but if I just continue the graph, it's going to get back down there, right? And to do it, let's check out this. So you can go forward by pi. Could I also go forward by another 2 pi and get to the same point? So that would be like 3 pi, or 5 pi, or 7 pi. Any odd number times pi? Oh, cool. An odd number of the form 2k plus 1, because that's what an odd number looks like, times pi. Neato. Feel pretty good? Let's play the same game for sine. What's the least value sine takes? -1. Can we start listing some inputs where sine is equal to -1? Well, I see -pi over 2. I see 3 pi over 2. Could I just keep adding 2 pi's to that? Yeah, so I think at x equals, well, it doesn't matter which one we start with. Maybe I'll pick 3 pi over 2 to pick a positive one, plus 2 pi k. Could I also have written down -pi over 2 plus 2 pi k? Would that give the same family of solutions? Yeah, so whenever you see these general families of solutions, there's going to be more than one way to write it. As soon as you find a thing happening for a trig function once, you can add 2 pi k's to get all of the times that that happens. If you pick a different forced time to check, you'll get different looking families of solutions, but they'll be the same family of solutions. Gesundheit. All right, even or odd. Let's look at sine forced. Even or odd. Let's see. Gesundheit. How do we check for even or odd? Let's check for even forced. A function is even if you can reflect it over the y-axis and get the exact same function back. Reflect this over the y-axis. Do you get the exact same function back? All right, so not even. How do you check for odd? Pin the origin and flip it 180 degrees around. So does that look the same as it did before? So is it odd? Nice. Oh, I see. I wrote cosine forced, but then did sine forced. Cosine, even or odd? I hear a call for even. People agree? Is it odd? Nope. In fact, there is only one function that is both even and odd, and cosine isn't it. This function is even. Could we figure out where these things are increasing and decreasing? Yeah, let's stare at the graph until we do it. Let's start at 0, and let's start with sine, because it's the first one. At x equals 0, does this thing appear to be increasing or decreasing? Increasing? Y values are going up. How long until it stops increasing if you start at 0? Pi over 2. So it's increasing until pi over 2. What's the left endpoint of that interval? Yeah, negative pi over 2. Guess I managed to read that one correctly. so maybe I'll label all of this as increasing. There's one interval of increase. Is that the only place where sine of x is increasing? Where's the next one? 3 pi over 2. And let's see, can you tell just based on the picture provided when it stops increasing? I guess not, but like, where do you think it's going to stop increasing? Well, you know what? I think it's useful here to have pulled up a Desmos demo. So let's take a look at sine of x. So you just found the interval from negative pi over 2 to pi over 2 where it's increasing. Then it's increasing from negative 3 pi over 2 until that value, which is 5 pi over 2, 3 pi over 2 to 5 pi over 2. And let's find one more, and then maybe we'll put some dot, dot, dots to indicate that there are infinitely many. So there's that endpoint. Any guesses where the next endpoint's going to be?
7 pi over 2.
Yeah, there's something to that, right? It looks like we're at every odd multiple of pi over 2. Cool. Where do you think this next one's going to be? Oh, well, I guess I spoiled it. 9 pi over 2, the next odd number. 7 pi over 2 to 9 pi over 2. Decreasing. Well, this should be easier, right? Are there any long stretches where sine of x is just like constant? No. So that means wherever it's like not increasing, it's probably decreasing. So it stops increasing at, oh, god damn it, Chris. So it stops increasing at pi over 2, so it starts decreasing. Pi over 2 until, when will it stop decreasing? 3 pi over 2. And then when will it start decreasing again? Five pi over 2, 7 pi over 2. That seemed pretty good. Let's just list one more thing because it's easy. How about taunting points? Do you remember what a taunting point is for a function? I mean, it's also just like a well-named thing. It's a point where the function taunts around. So it's a place where it stops increasing and starts decreasing. So based on what we just found, tell me some taunting points. Pi over 2. Give me another one. Negative pi over 2. I want them listed in order, so I'll put them in that order. Next one. 3 pi over 2, where it goes from decreasing to increasing. Oh, interesting. So what do you think? Every odd number times pi divided by 2? All right, cool. Same thing for cosine. And maybe we'll even just start with the taunting points. Tell me the taunting points first. So there's the graph of cosine up there. Where's the first taunting point you see? X equals 0. It goes from increasing and then it starts decreasing at 0. Where's the next one? Pi, I guess? It turns around at pi, it goes from decreasing back to increasing. At 2 pi, it goes from increasing to decreasing. Let's also list some negative ones. Are there any negative taunting points on this graph? Where are they? Negative pi? Oh, so I guess I could just like put a plus or minus there. Negative 2 pi? All right. And I know there are some not on the graph. Where do you think the next taunting point is likely to be based on that pattern? 3 pi? And also negative 3 pi? All right. So I'll put a dot, dot, dot there because the pattern's clear. Groovy. We feeling all right? So there's one thing you can just read off from the graph of sine and cosine. All the same things that we could before. Is it even? Is it odd? Where is it increasing? Where is it decreasing? Where are its maximum values? You can read off all the standard stuff from the graph of sine and cosine. There's one other phenomenon that trig functions have that is not represented by anything we've seen previously in this class, and that's periodicity. So a function is called periodic if there's a non-zero number p, so that when you add that number to the input, you get the exact same function back. And it's called periodicity, and p is the period, because this function just has the same behavior over and over again. Let's try to determine the period of cosine of x by looking at a graph. So, this link, which I don't know how to make walk using just that, but I have it pulled up, will take you here. So, here I see the graph of cosine of x, and y equals cosine of x plus a constant. I've multiplied the constant by pi because it's a number inside of a cosine that should probably be pi next, right? There's a better reason, but like. So let's start tweaking that number c, starting at 0. And let's just start ratcheting that constant c up until the green graph lies exactly on the red graph again. And right now it does, but the constant is 0. The period is the smallest positive number where this happens. So let's continue on. Oh, that's too fast. So let's get to 0. And let's start going forward. So as that constant goes up, the graph shifts to the left, but you know that's what it should do. And it looks like right about there, it lands on top of itself again. So if I add 2 pi to x, I get the exact same graph back for cosine. So what's the period of cosine? Well, 2 pi. I put the extra pi in there to make it. Otherwise, how would you have guessed that something around 6.4-ish is 2 pi? So it sure looks like the graph of cosine is 2 pi. And I guess that makes sense from the unit circle point of view. If you rotate forward by some angle, and then you also rotate forward by that some angle, and go around the unit circle one full extra time, do you get to the same point? Yeah. So these things should have period 2 pi. Any guesses as to what the period of sine of x should be? I hear an also 2 pi. Does that seem likely? Let's pull up the graph and just check. Let's replace these sines with cosines and see what happens. There's the graph of sine of x. There's the graph of sine of x plus, you know what, let's just force that to be 2. It seemed like the same graph again? Nice. Also 2 pi. Oh, and I didn't do anything fancy. I wrote down 2 pi. All right. That feel pretty all right? So, we know lots of things about trig functions based on that. Let's do one more thing with trig functions. Oh, and let's start with the same thing at the top. One of those is sine, one of those is cosine. Which one's which? First one is cosine. Second one is sine. Those two graphs look pretty similar to each other, right? Sine of x and cosine of x, they basically look like the same graph. But like, maybe sine is cosine but shifted by a little bit. Or I guess I want to say cosine is sine but shifted by a little bit. Shifted by how much? Maybe here's a way to check. So these horizontal shifts won't change y values. They'll only change x values. So let's find some x values that seem to have the same y value. There's a stretch. To go from this green value to that green value, how far do you need to shift and in what direction? Left by pi over 2. So to go from here to there, maybe we want to go left by pi over 2. Does that same shift walk to get pink to pink and blue to blue? Cool. So it looks like cosine y equals cosine x is y equals sine x shifted left by pi over 2. That's the conclusion we just made. How do you compute the function left by pi over 2? You add pi over 2 specifically to the input. So, that sure seems like the cosine of x should be the same as the sine of x plus pi over 2. Let's do a quick check. There's sine of x already. Sine of x plus pi over 2. Let's have it actually graph. Here also is the cosine of x. Seem to be the same graph? All right, and we already knew they should be, but it's nice to have it, compute or do a bunch of computations to check. So there's an interesting fact. Sine and cosine are basically the same function. One of them is just the other shifted by pi over 2. Could you also do the same thing to write sine as a shift of cosine? I guess instead you'd shift to the other direction. So here's something that's not surprising. Sine of x is cosine of x minus pi over 2. Because, right, that's just the same fact as above. Nice. So we have this concept of periodicity. Trig functions have a period of 2 pi. Whenever you have a periodic function, you can also talk about the amplitude, which measures how high up these periodic functions get and how low down they get. In particular, it measures the difference between them. It measures like the total wiggliness between the peaks and the valleys. And here's a definition. Amplitude. The amplitude of a periodic function is 1/2 the maximum value those periodic functions take minus the minimum value these periodic functions take. All right, well, let's look at those things on the top. So let's do this for, should we do it for sine or for cosine first? For sine? For cosine? Cosine it is. So, let's compute the amplitude specifically of cosine of x. Well, I guess, okay, there's good motivation right there. What's the maximum value cosine takes? 1. So there's a 1/2 because of that 1/2. Maximum value is 1. What's the minimum value cosine takes? -1. So what's the amplitude? Almost. It's 1/2 of 2. So what's the amplitude? 1. So a thing to remember when computing amplitude, there is that 1/2 there. And I guess one reason it makes sense that it should be 1/2 is, what if instead of asking you for the maximum minus the minimum, what if I asked you, what's the difference between the maximum value and the average value cosine takes? I haven't told you what like the average value should mean, but if I asked you on average what is cosine equal to, what would you tell me? I'm going to make an argument for 0. It's like above y equals 0 exactly as often as it is below y equals 0. So its average value is 0. And that's something that you need some more complicated things to really make sense of. So what's the difference between the maximum value and the average value? Then it's 1. 1 minus 0 is 1. So you can get the same thing by taking max minus min over 2. Same question for sine. What's the amplitude of sine of x? 1? Nice. By the exact same walk. Max value is 1, min value is 1, 1 minus negative 1 is 2. Divide that by 2 to get 1. All right. So, the last thing I want to do for just sine and cosine, you'll notice I've totally ignored tangent, secant, cotangent, and cosecant. They'll appear on the next page. Let's do one more thing with sine and cosine. Let's talk about graphs of transformations. So let's suppose I wanted to sketch the graph of minus 2 cosine of negative 2 thords x minus 2 plus 3. Is that something that we know how to do? Yeah. Let's see. I guess that means I should start with just y equals sine of x. And I'll pick out some particular points. It goes to the point 0, 0, pi, 0, 2 pi, 0, and maybe I'll pick out this peak, pi over 2, comma 1. And now I need to do some transformations to it. Do you remember what order we're supposed to deal with the ingredients of transformations in? Yeah, I guess like opposite what you would expect from order of operations. You walk from the outside in. So first you deal with this one. What does that do to the graph? So it multiplies all the y values by negative 2. So it'll flip it and then stretch it. So y equals negative 2 sine x. Let's go through these like 4 special points. Where does 0, 0 go when you double the y value and multiply it by negative 1? Still 0, 0. Where does pi 0 go? Well, you only change the y values when you do this, right? What's 0 times negative 2? Still 0. So there's still this point at pi 0. Still this point at 2 pi 0. Pi over 2, 1. Where does it go when you multiply the y value by negative 2? Yeah, it goes, to the bottom. Pi over 2 comma negative 2, I guess. And I'm not super worried about having correct scale, but neato. So there's the graph of sine of 2x. What's the stuff I'm supposed to deal with next? The plus 30. Could I deal with the minus 2 at the same time? Yeah. And maybe just in the interest of space and also time, let's do both at the same time. All right, what is that going to do to the graph? What does the plus 3 do? Moves it up 30. What does the minus 2 do? Moves it to the right by 2. So all the x values need to get 2 added to them. All the y values need to get 3 added to them. All right, let's do that. 0, 0, where will it go? 2, 3? Pi 0, where will it go? Whatever pi plus 2 is, then plus 3, so I guess that's 5-ish, comma 3. All right, and let's track this point also. Where will it go when I shift it right 2 and up 3? Well, it'll go right 2, so the x value will get 2 added to it, so it'll become pi over 2 plus 2. The y value will be negative 2 plus 3, or 1. Pi over 2 plus 2, comma 1. And then the whole graph will look the same as it used to, but shifted a little bit. I'm not going to worry about having the x-intercept, y-intercept. Does it look like this has an x-intercept anymore? Which is fine. Things don't need to. Here's the final ingredient. What is that 2/3 going to do to the graph? Negative 2/3. All the x values will get divided by negative 2/3, which is the same as multiplying by negative 3 over 2. So let's do that. All the x values will get multiplied by negative 3 over 2. So where does that point go when you multiply it by negative 3 over 2? The 2 will become a negative 3. All right. So that point 2, 3 will become negative 3, comma. What will the y value be? Does the y value change when you do this? So y value is still 3? And now let's just do the same thing for all the rest of them. And then it will generally repeat. Maybe I'll pay attention to where that is. So 2 pi times negative 3 over 2, negative 3 pi plus 2 will become plus 3. No, that will become minus 3. Same y value, 3. And then it'll repeat. And here's the final thing I want to point out about this. Is that still a periodic function? Is it going to keep wiggling up and down at some frequency? Let's compute the period and the amplitude. So I guess the period is that length. So what's the period of this function? The coordinates are hard to read at this point, right? Negative 3 pi minus 3 minus 3. So what's the difference between them? 3 pi. And the period by convention should be positive. So what's the period of this function? 3 pi. Oh, I guess I also need this. The max value of this thing will be at y equals 5. So what's the amplitude of this function? It's almost 4. You're off by one thing if you want to say 4. What's the max value? What's the min value? 5 minus 1 is? Divided by 2? 2. So here's a general fact. Oh god damn it, that's in the wrong place. Period is 3 pi, amplitude is 2. There's something else that's going to go there. The next formula is going to tell you how to compute the period of such a thing without doing all this hard walk of graphing it. You can just read them off. And we'll start with that next time.